o'clock, and I welcome everyone back to lecture number 3. We're going to talk about long wave today, and then hopefully I made an outline here today of the objective for the next 50 minutes or so to get to total net radiation. Before I start, and then so we're somewhere in here, we get these to go. I made a small error, and people say there are no small errors. There's no small typos. There are typos. Yesterday, when I did this, we have 1,000 in, and 50% reflected, so 50% was absorbed. So this shortwave in was 500, that's correct. This reflection right here is 100. And I said, well, we have 100, that means 600 watts are absorbed. But some people correctly said, wait a minute, this 100 is also times 1 minus the albedo. And so this really is 50, and the correct answer is 500, not 600. 550, thank you. This is over here. 500 plus 50, 550. And this 50 is quite a bit of energy, so it's not really a small error, but it's important that this is correct, because sometimes this reflection is huge. If you get something on the south side of a building, this reflected energy can be a lot more than 10% in some cases. In this example, it's not so big, but it depends on the case. So we've got this diagram up here with arrows in and arrows out, and this is a pretty messy diagram, but it's useful to have diagrams like this because it helps you keep track of the inputs and the outputs. So some years ago, we made this diagram, and I have this as a handout, the inputs and the outputs. I need to go up just slightly to see the whole works. There it is. And all this is a nicer diagram of this. I guess the sun's on the right-hand side now, but solar in, with this arrow we've talked about. Oops, sorry, this is sky radiation coming in here, which we didn't talk about yet. Here's solar in, some bounces off, here's reflected, same thing. These big fat curvy lines are what we're going to talk about today, long wave radiation, calculating these. And then of course we got outgoing transpiration, conduction, convection, and here's some long wave components here coming into the leaf. Long wave means the wavelengths are long, and so we draw those with curvy lines, and short wave is the wavelengths are short, so we draw those with straight lines. And then finally here's soil heat flux when we calculate that. So a diagram to keep the components straight, and then the goal then in a quantitative sense is put numbers on the arrows and add them up, make sure it balances. This issue of a diagram is something that everybody that teaches this makes some kind of their own diagram of their own. And here is Park Nobel's diagram of exactly the same thing out of this chapter that we're using. It's slightly different arrows, and it's in some ways these real fat arrows for infrared radiation kind of overemphasize. If you scale these to the rough size of their numbers, the biggest arrow in here would be direct radiation right there coming into the system. That's ultimately what drives the whole thing. But these are diagrams to help people see this. So here's the one I love. So I read this stuff. Every time a new textbook comes out, I read the chapter on radiation, and I think, oh, that's a nice diagram, and this explains it a little better. And, you know, I keep thinking of other ways to teach it. But one of my favorites is the textbook that we use on campus, Animal Physiology, the 3rd edition. So you turn to chapter 16, Animal Energetics and Temperature Relations. And this is not just metabolism, because respiration's big in animals, much bigger than people, but so is all the fluxes of long wave. So you turn the page to this author's diagram. This, I just love this, a hippopotamus with the exact same arrows reflected. He's got a little tiny bit of evaporation, infrared thermal radiation. So the point to this is, everybody's got their diagram, and once you get these principles, you start applying them to everything. A hot tool laid out in the sun and how hot it gets. You can even calculate how fast your laundry will dry on the clothesline, depending on the wind speed and solar radiation from this. So, where we left off, oh, I have one more diagram I want to show you before we get there. A couple from the book to link this to the book. Here was my picture yesterday of shortwave and all the components, and then this big clump of thermal long wave. So Park Nobel has that diagram as well in the book, only I like my diagram a little better than his because he shows the same thing, but he has it on a log scale. And I'm not a big fan of log scales for teaching because they distort things. So look at his infrared radiation by the leaf. It looks like this sharp peak. And if this was not a log scale, it looks like this. But it's the same data, direct solar, and he has some reflected skylight in here. And then he also shows wave number. Wavelength is simpler, but it's still relative fluxes, and if you look at it long enough, it's the exact same diagram, just log scale. He also has this diagram, which was on the bottom of one of the handouts for this Stefan-Boltzmann equation. Radiation emitted in watts per meter squared and surface temperature. An important thing about this is a nice big diagram, but if you put a pencil on here and you put a ruler on here and you put 25 degrees, you're pretty close to 400 watts per meter squared, which is useful to remember because we're talking about 1,000 here, but we're talking about fluxes of 400 in long wave, so they're not trivial fluxes at room temperature. So this would all be terrific if we just calculated temperature, we multiplied it by the Stefan-Boltzmann constant, and we could get our long wave radiation. But in the case of long wave radiation, not everything is a perfect black body. Not everything is perfectly black and radiates at black. Some shiny objects do not emit long wave radiation very well at all. So we get an additional symbol in here, it's lowercase e, called emissivity. Emissivity is 1 for a perfect black body, and the opposite extreme is a piece of tinfoil, the best common thing I can think of that has a low emissivity. And somewhere right here, I have a piece of tinfoil to emphasize this point. And here it is. And I'm gonna, now we have two things that are confusing. Albedo, which refers to shortwave radiation, reflectance of shortwave, and then this thing, emissivity, which only refers to long wave radiation. And again, long wave is warm objects, all objects that are less hot than the sun. In our environment, the only thing that's any significant source of shortwave is sun, and then all the terrestrial objects are all back and forth long wave. So I'm going to put this up here. I'm going to erase this. This is pretty straightforward. We've got it. 3 objects. And my goal is that 10 years from now, you'll still remember this little demonstration and it'll stick in your head and you'll have it forever. Tin foil. Aluminum foil. Where's my marker? Albedo. Pretty reflective of shortwave radiation. So we might say, and it depends on how perfect the tin foil is, if it's got crinkles, but if it's pretty perfect, it's going to have an albedo of 0.9. You can look this up in a book to see exactly what people claim for this, but it's high. Now let's do, just doing albedos for a second. Black paper. Albedo 0.1. Might even be blacker than that, but 0.1. So now we do white paper, and instead of drawing a square, I'm putting actual white paper up here. It's white paper. And if this was a test question, 100% people would get this right. The albedo of this is about 0.9. Plus or minus 0.05 or something for these. Okay, now let's do, right below this, giving ourselves plenty of room to see it, emissivity. Completely different concept. This is reflected, this is emitted from the surface. So this, as the surface gets warm, it's the ability to give off long-wave radiation. A black body, this, depending on how black it is, this might be 0.9 for the ability to give off. Now, white paper, what do you think white paper would be? Well, hardly can emit, right? It's the opposite of black? No. White paper might be 0.85, maybe even 0.9. A white surface is a fine emitter, similar to black. But now let's take a shiny surface, any kind of polished metal that's shiny. The emissivity of aluminum foil, 0.03. That's a clean piece of aluminum foil. Shiny surfaces are poor emitters. So what does this mean for energy balance? If this was hot, and again, let's imagine we're on the moon where there's no air, because it simplifies it. We put this on a stove, we get it hot, we lay it out. It would take forever for this to cool off by emitted radiation. We heat, this is a block of metal now, right? So we take another block of metal that's black, heat it up exactly the same, lay it out, it cools off right away. Same thing with white. They cool off right away because they can emit that radiation into space, into other objects on the ground. And the moon simplifies it because there's no transpiration, conduction, and convection. So this little diagram helps to emphasize the differences in emissivity. And now we are going to sacrifice part of this leaf right here to science, because the thing we're after is leaves. That plant just gave part of its life for science. Typical albedo of a leaf, and I'll put this one in green, 0.25. Not intuitive. It's in greens in between black and white, but has a much lower albedo than white paper would. Emissivity of a leaf, not completely intuitive from this, but the typical value we use for a leaf is 0.96. Very, very high. Leaves effectively emit radiation, which also means they can effectively cool off as soon as they get hot. It's worth putting on here one more thing. Let's see, I can erase this. Water is blue, right? So now we're going to put a blue square, right? It's full of water, all blue. Water has an emissivity of about 0.96, maybe even 0.98. And this is why biological objects that are full of water, like our skin, have very high emissivity. That things that are hydrated and wet effectively emit long-wave radiation. The albedo of water depends a lot on sun angle. If it's low sun angle, you get glare and a lot of reflectance. And it depends on how clear the water is. I'm not going to put a number in here for albedo, but the point is water is a really effective emitter of long wave. So there's the concept of emissivity. And one of the things that I think of when I'm thinking about this is if we're designing wood stoves to heat the cabin somewhere, we would not want to build the wood stove out of aluminum foil. It'd be terrible. It'd sit there and get hot, and if you walked into the room and tried to find that wood stove, you wouldn't tell where it is. But wood stoves are black, and they're effective emitters. So as soon as a wood stove gets hot, it's giving off its heat to the room. So you would think there's a lot of things in between here, between these two for emissivities, and there are, but not as many as you might think. All polished metals have low emissivity, but most building materials, bricks, white walls, stucco walls, are all up in a higher emissivity. The only things that are really low are shiny objects, but they're a nice example because they're really low. So why don't we just, well, gee, you just told us we can ignore photosynthesis. Why don't we round this off to one significant digit and just call it 1? Yes, we would if this was radiation physics 101, but this is radiation physics 501, and this number matters. It's multiplied by hundreds of watts per meter squared. So small changes in this multiplier make a big difference for energy balance, and it's worth putting those numbers in. By the way, snow is like this. Good emitter of long wave and reflex short wave. I've never actually taught this with the live leaf taped on the board before, but it helps show the concept. So now that we have this, we can start to assemble our energy balance model with all the components of long wave radiation in addition to short wave. Because we just ran our model and we'll erase some of this. And we will say, in red, radiation, short wave, comma, absorbed is 550. Now we'd like to do radiation, long wave, incident. First incident on the leaf. How much is coming in? This line is incident on the leaf. How much long wave is coming in? There's two sources of our long wave, particularly since our leaf is a flat leaf above the ground. A nice simple example. So here's our flat leaf right here, and I'm going to even take that part off. So we have ground shown in black, long wave coming up to the leaf from the ground. So let's say the ground, now I have a handout that assimilates these, and I'm going to give you, and I'm going to want to follow the same numbers. We have to assume a ground temperature. Measure it or assume it. And in this case, I assumed 27 degrees C for the ground. So now we plug that number in, and if I'm lucky, I can find my chart of long wave chart from yesterday. Where'd that go? Anybody have that handy? That's the table of yeah, you can look it up, but I want everybody to, thanks, follow along. Here we go. The ground's 27,460, but so 460 for this part right here, 460 T to the 4th Kelvin. But we have to measure or assume an emissivity of the ground, and we're going to take, I don't have a lot of room, but you can see it here, times 0.9 for the emissivity of the ground. So that radiation going up is 414. All these units are in watts per meter squared. So that leaf is absorbing, or is getting 414 from the ground. Now, it's a horizontal leaf, so it's also getting radiation from the sky. So you would think the sky temperature on a warm day the air temperature might be 27 degrees C, and you would think, well, about the same as the ground then. If the air molecules are 27, we could do the same thing and there'd be 414 here.
There's no long way from the sun directly.
Correct. The question is, well, how much long wave is from the sun?
Everything I'm looking at shows no long wave.
And the answer is no. If you take a radiometer, good radiometer, and point it right at the sun, you get the same temperature as the open sky. Yet none. It's just amazing. And it's so counterintuitive, you almost have to walk out with the instrument and say, that's baloney, I don't believe that. And point it at the sun. So after class, take an instrument and go do that test and convince yourself. It's just amazing. All that sun is shortwave. So, but that's the shortwave is one dot in the sky, and the whole rest of the sky is emitting. But even though the air molecules might be 27 degrees C, radiation, the atmosphere is pretty transparent to long wave. And if it was perfectly transparent, like say on the moon, it would be 0. Outer space is 0 Kelvin. It'd be 0, but we don't get 0. We make careful measurements of this, and we get cold sky temperatures somewhere in between room temperature and 0, and we call that the effective sky temperature. And it depends somewhat on elevation. So it's colder skies at high elevation because there's less air. It depends on relative humidity a bit because the water vapor molecules affect it. But typically, from a sky, we'll get 300 watts per meter squared. Now, that's a clear sky. So, did we use this to get the clear sky? Well, what's the effective emissivity of the air? What's the effective temperature? Both of these interact to give us this number. So this is generally a measured number. It doesn't depend on air temperature. It just depends on how clear the sky is. Clouds, let's take a case with clouds. I'm going to get rid of this. 0. Clear sky, which is what we're doing this model for right now, clear sky. Now we go over here, clouds. And it doesn't have to be a black thundercloud. It can be a perfectly white, nice cloud in the sky. Now we go out with our instruments and point it at the cloud. Clouds are relatively close to the Earth. They're full of water vapor. So now we are, in fact, reading the temperature of the water vapor molecules in the cloud. And pretty often, a cloud will jump up to, maybe 400 watts per meter squared, because it's close to the ground and the molecules in the cloud are warm, and we no longer see the infinity of space. So, and if it's a real heavy cloud, this can get all the way up to over 400 for cloudy. So there's a big difference between cloudy skies and sunny skies for long wave radiation. So everything else we do from the emissivity of the surface and the temperature, but clouds and sky temperature, we just measure them. Now, it's been measured many times, and so we know approximately what they are. So let's start adding up these numbers now for radiation in. We get 550 absorbed. Now, this is, let's see, 414 plus 300 would be 714 watts per meter squared radiation. But there's one other calculation. 0.96 is the emissivity of a surface, but this is an important thing. I'm gonna put it right here. Emissivity equals absorptivity. RP E equals A. This means that if a surface is 0.96 for emitting radiation, it's also 0.96 for absorbing that same radiation. So if 714 is coming in, let's put this right over here. 714 in, we have to multiply that by 0.96 for the leaf, for the absorptivity of the leaf, and that comes out to 685. And that number is the energy absorbed by the leaf in long wave. This is radiation, long wave, absorbed in this example. Now we sum that, 685 with 550 here are long wave absorbed 685. So the staggering message is, wow, there is more long wave absorbed by that leaf than short wave. The sun is hot, you go outside and you think, wow, this is it, how can this be? This is hot. Now what's the sum? thank you, 1235. So maybe in radiation 101 you would say, wow, they have to evaporate enough water to get rid of this energy. But long wave works both ways. All this long wave is coming into this leaf from the ground. But wait a minute, what's the leaf temperature? And I assumed a leaf temperature of 25 C. Now, how much is leaving that leaf by long wave? And we look up on our chart, 25, 448. Let's see, I'm going to put this over here. Here's a leaf, 25, 448 times 0.96, right? So it's a little less than that. 430, 430. So you say, whew, good. We can subtract 430 from this, and the leaf doesn't have to evaporate so much water, but it gets even better than this. Radiation doesn't just go down, radiation can go up too from the leaf, both up and down. So the downside is 430, and the up is also 430. So radiation, long wave, emitted is 860 watts per meter squared. So, let me erase some older stuff here. So we start to do a sum of this, and we have radiation absorbed, total radiation absorbed, 1235. Radiation emitted, 860. So, and this is out, so we subtract it, 300, thank you, 375 watts per meter squared. And that's the final answer, no other add-ons. This is how much water that leaf has to evaporate to stay at air temperature. So big numbers coming in, because this is short wave and long wave, but big numbers going out too. And if you think about this energy balance right here between the leaf and the ground, if ground and the leaf might be close to the same temperature, so this is always fairly tiny, the net between the ground, but the sky is colder than the ground if it's clear, so we can lose energy by long wave radiation to the sky. And that helps on a clear day. It helps keep leaves cool because they're emitting to the clear sky. So these are the components, and what we calculated was, well, we didn't explicitly do net long wave, but we could have. Here's 685 in and 860 out for long wave. And so the net long wave is a negative number. And it is always a negative number. If the sky is clear, we're losing more long wave. We're losing heat by long wave. So, having worked through this, step by step, using the same inputs as this, here's a worked out example. And thankfully, with your help getting done the math, we got the same number as the worked out example. So it means either we had corresponding errors or everything's correct. But these are the inputs and outputs that you always use to determine radiation balance for any object, leaf. And these numbers are all big. The stuff coming in and going out is big. You would think maybe we would like to have leaves kind of like tinfoil. Why didn't they evolve like this? Well, they can't get rid of, once they get hot, they can't get rid of the heat. That would not be so good because they're shiny. It's better to have leaves something like this, and they're not absorbing the heat in the first place, and then they're emitting long wave to stay cool. So I'm thinking about this and teaching it over the years, and I'm thinking about how do you give examples to drive home the power of long wave radiation. And I'm going to give you, let's see, I'm going to take these down. There's more room up here. What if, well, this is a well-known thing from Boy Scouts. If it's a cold, clear night in the mountains, go sleep under a tree. You'll be warmer. And the Boy Scouts are all, you know. But if you went out there and did the net radiation, the tree is way warmer than sleeping outside under the clear sky because of the radiation. I don't have one with me, but if I did, it would be a great example. A space blanket. You know, how can they help you? They're thin. Wow, they help you doubly because they're shiny on both sides. So your body heat gets reflected back in, and this does not emit to the outside. That's why space blankets are so effective. It's nothing to do with conduction and convection. It's all radiation physics, keeping the warm temperature in. People say, yeah, you know, my grandmother always says, put the dull side out and potatoes in the oven. You can read on, people argue about that stuff online. It turns out it just doesn't matter. The dull side is really close to the outside, and you know, they're both low emissivity sides. So if this is the case, why do you wrap potatoes in aluminum foil? Because, geez, I mean, the radiation from the oven is not contributing to heating up the potato. To keep the moisture in for the potatoes. This is very effective to keep the moisture in, even though it makes the potatoes cook more slowly. But that's all radiation physics in the kitchen, and we can go on and on about all the cool examples in a kitchen of cooking food and radiation physics. How fast is my food going to cook in an oven? What's the walls of the temperature of the oven? There's no shortwave in an oven. It's all radiation physics, and it's helped now with convection ovens. We turn a fan on so we get some convection in there. But here's the example that drives home the power of long wave radiation. And I'll draw a diagram of this, and then you can tell me what you think is going to happen. We're going to build a box or a cylinder, and we'll make it out of blue styrofoam, something that's a very effective insulator. And a couple feet tall. And in the bottom of this, we're going to put a bowl with water in it. Thin layer of water. And by the way, the bowl's painted flat black. The surface of the bowl's painted flat black, water in it. Now we take this outside. It's a simple device. Take this outside like tonight. It's hot, but the temperature might get down to 20, 25 C tonight. We take it outside under a clear sky, and it's calm winds. What's going to happen to the temperature of that water? to room temperature when we brought it outside, it's going to radiate to the infinity of space, and the whole inside of this is going to radiate to the infinity of space, and it'll get colder and colder, and conduction and convection can't warm it back up because we have a big insulated cylinder, and if it's windy, we could put a piece of cellophane on there. Real thin cellophane transmits long wave. But it works good even without this. So now it gets colder and colder, and it's radiation's coming in from the sky, right? But it's a clear night, and the sky temperature, I put 300 as an average, but around here, and I've got some examples of this sky temperature can be more like, I don't know if I've seen 200, but 250 watts per meter squared. Mark, do you remember low numbers from sky there?
You can definitely get 200.
It's so, let's say 250 for summer. Now, radiation energy, we have to follow the first law of thermodynamics. So energy in equals energy out. So this keeps going until these two arrows are exactly the same size. And if 250 is coming in, 250 has to be going out. What's the temperature of the water? On a hot summer night in Logan, if 250 is the emitted radiation. Oop, I got to put my, back to our table. The water freezes. It easily freezes. And this is so counterintuitive, it would freeze even if the sky was 300. It'd get below zero and the water would freeze. That is the power of long wave radiation. So this is so cool. After I thought of this, I had to go do it. And this is my house, my backyard patio. We'll zoom in on this so we can get this really big in here. And I got some blue styrofoam. I did it once and it didn't get super cold, and I kept doing it, and I got bigger layers, and I made this longer. You can see a fine net radiometer right up here, so I can see how this is coming along. And you can tell this is a long time ago because this is like an old 8088 computer, and this is my daughter, who is now 26 years old. And little pump to inflate the domes and that thing. And right in here is a Campbell Scientific data logger with thermocouples in the water and thermocouples all over. And I'm watching a very primitive graph of the temperature in this thing. And my wife came out and took a picture. And it wasn't dark yet. It was, you know, the sun was just setting. I never got that water to freeze, but I got it to like 1 degree C. It was pretty cold. That's radiation physics. And in fact, this is such a powerful principle. The reason I thought of it is because people make refrigerators in the tropics just like this, and they open them at night, and they have blocks of water in here, and if they get cool in the day, and they're cool at night, and then they close them in the day. And you can keep food cold just by radiation cooling. In fact, you could run this in the day if you kept pointing it away from the sunlight, because the sky is clear in the night and the day. I have a couple of other examples of this. And since this particular audience is instrument intensive, now we'll show some actual data. And I gotta zoom out just a bit. There we go. This is some data. I gave this as a test question. to students after I talked about these principles. This is last winter, January 11th, it's 1 week to January 17th. This is on campus, net radiation, and first of all, it's measured albedo, because we have radiation in, radiation out. So what you need to know here is on these days, the snow had melted off and it was basically grass, mostly dead grass. It's January, but it wasn't snow. So what did we say the albedo of grass was? Maybe 0.25. Hard to see on this scale, but there's about 0.25 for these days here. Then we had, these are night, by the way, in here. It's just zero in, zero out. Then we had this big spike that went to 2. And if you weren't an instrumentation person, you're going to go, wow, 2 times as much shortwave radiation leaving as coming in. So what could have caused that? This giant spike right here. Now, if you're living in the area, you would remember what the weather was like, but here is why that thing spiked up. This is Peter Sinks, about the same time, and there's a bunch of snow. This is a Huxaflux net radiometer. Shortwave in, long wave out. Guess what? The shortwave in's blocked, so of course it goes to 2, because the bottom one is not blocked. So we get issues like this, and you just have to understand the things that give you bad data and filter them out of the data set. So, but I wish if I was a little more organized, I'd show you the exact picture of the campus station at the same time, because it happens every time it snows. You get stuff in here. For that reason, we put heaters in sensors whenever we can. Heaters are expensive, so it's hard to run them off of solar power, and then when it snows, you get snow in your solar panel, and it's tough. But here is a little silicon pyranometer with the heater that kept reading correctly during that snowstorm. So if we would have had 2 of these in that system, we would not have had this artifact right here, this albedo of 2. But okay, right here the snow melted, and it's a little not completely melted. Now look at the albedo of this surface. No snow, snows, 0.8. So the snow did what it should. It reflected shortwave radiation. And then we got some, I think we got more snow, but it jumped from, is a nice example of no snow and snow on the ground. Here's some numbers for incoming long wave. So Mark said we can get down to 200 in the winter. Well, there we go. That was a very clear sky. The long wave was 200 watts per meter squared. Here's a cloudy sky, and we're up around 320. And whenever it gets clear, the sky gets cold. Outgoing long wave is just based on the temperature of the ground, and that's this purple line. And you can tell the temperature of the ground because the outgoing long wave was 280 to 300, which is right just slightly below 0. The surface of the snow up there was probably -3 degrees. So these graphs are on the internet, and I'm going to put the location right here, because as soon as you know the principles, you can watch these graphs and say, yeah, that's why this is working. They're at weather.usu.edu. This is a whole series of graphs of all these principles. There's many more, but this is one of them. And I use these all the time as test questions. They say, here's the weather last week. Here's what was going on. Explain this graph. Why'd this go up? Why'd this go down? And you get to look at ratios of different graphs to see what's going on. But it's really helpful to drive all this radiation physics into your head to see examples of it. this is the same time period. It's a different graph, but ground temperature, equivalent sky temperature. That's what we call it. This sky temperature up here is the equivalent of minus 22 C. It's the combination of effective emissivity and sky temperature, and we call that equivalent sky temperature. And then net is just the difference. And of course, whenever the net is a really low number, that means it's a clear sky. And look at this. 0 cloudy skies. Lots of clouds in this period. The net radiation was 0. The clouds were just as warm as the cold surface in the winter, or in the heavy clouds. Now, let me, here, I don't have a handout of this, but I'm always looking for teaching examples. Here is, can move this up a little, a picture, here, to be really right, I put that part off. There's a picture of a stone. It's a little bit glary, but this is all snow. This is in the middle of winter. I'd like to tell you this was up Logan Canyon, but it wasn't. A dark rock, and look at the melting of the snow. Here's the shadow of the rock. It's a bright day. Here's the melting of the snow right around the rock. What made that snow melt? Reflected shortwave. Oh, wait a minute, the rock is really dark. There's hardly any reflected shortwave. Every day, that rock absorbed the shortwave like crazy and got warm above the air temperature, and all night long is emitting long-wave radiation and melting the snow. So this is long-wave radiation melting the snow from a warm rock, not reflected shortwave radiation. That's what, then I put that down here, long-wave radiation emitted from a stone. And you can see it's not super warm. It's probably melting this a few millimeters every day until it snows again. But it's warm enough to melt the snow by the long wave. Because net radiation is such a big factor in everything with energy balance, and because, by the way, now we have simplified, all this stuff feeds into one thing, and we'll put it up here. This is good. Now our whole equation goes to R net, and this is absorbed, equals T plus C squared. All those components that feed into this give us one number. And so to put numbers on this, 375 equals T plus the sum of T plus C squared. So once, this is a tough number to get at because of all the factors we talked about, but once we get it, wow, there's only two components that can go into this. So this is the theory, but not surprisingly, companies have built instruments to measure this number, to make this easy, and to help people understand those instruments, we made another refrigerator magnet. And you can put it on your filing cabinet and look at it, and every time things seem a little goofy, and this has got two sides. I think this is, I can zoom in a hair, two sides, summer and winter. And it's great because these fluxes are so different. And it's got short wave and long waves. All these principles we've been talking about for 2 days are all right here. 1,000 in, now 200 out. So the albedo is 0.2 in this example. Nice round number. The net for this is 800, because some's reflected. Here's long wave, 450. So this is roughly, what would 450 be? 24C or something, right around there. Sky, 300. Net, minus 150. So net and net, 650 watts per meter squared for a fully vegetated surface. So in this case, this is not a single leaf. We do not have transmitted radiation to the ground because it's fully, all those leaf layers are all absorbing it. We also don't have two sides to radiate radiation. Here it was radiating down, but here the ground and the leaves are the same, so we got to get rid of 450 watts per meter squared in the summer. Winter, much lower input. You can see the sun, anatomically correct sun, sank in the sky a little bit. 400 in, snow, 350 out. Now the net's only 50. In the winter, no wonder it's cold in the winter. Long wave, the snow is cold, so only 300, and a little bit less long wave from the sky. Net 50, or net plus 50, net minus 50, 0. So it's not warming up on days like this in the winter, largely because of the snow cover. Then we finally get some warm air to help melt the snow, and then the whole warming starts. But this little refrigerator magnet helps it understand the magnitudes of the fluxes in two very different conditions. So it's been helpful. I'm going to stop here and pick this up tomorrow when I think at this point the next thing I want to do is apply this to the whole planet Earth for energy balance on the Earth, because we're an independent system orbiting through the vacuum of space. We are not losing heat by conduction and convection. The Earth isn't. We're not losing or gaining heat by transpiration. The water we have stays in the Earth. All we have is radiation physics to the rest of the universe. So if that doesn't balance, if this whole thing, if net radiation isn't 0.00 for the Earth, we're either going to cool off or warm up. So now that you have these principles in place, now we can take and look at the fluxes for the whole Earth. And this, in a nutshell, is the essence of global warming. And I think I can explain to you why that's complex, why the smartest people in the world are doing global warming right now to try and see, is this number really 0? You know, and how far off of 0 is it? And it's all radiation physics. So I'll stop here. Dirk.
So this is probably getting into noise, but a lot of, well, everything we've talked about so far is assuming effectively the surface of the leaf is normal to the radiation. So, I mean, is that even something that's considered anywhere?
That's not noise. That's the subject of many PhD theses.
Oh, sure.
It is.
The noise for this discussion.
And yeah, well, you got to start with one thing that we understand really well, and then you say, okay, here's that leaf. Now we're going to tilt it. And now what happens? So the first thing that happens is multiple tilted leaves don't reflect quite as much. And as we just said here, the transmission to the ground is much less. But it doesn't affect it as much as you might think, because you still have reflected shortwave, and the long wave is just from the surfaces. It doesn't matter that they're all vertical surfaces and it's going like this. Eventually it goes up. So one flat leaf has the same effective radiation as 100 vertical leaves, as long as they're covering the ground. That orientation doesn't matter for the emission of long wave. Same thing for absorption. It comes in. The biggest thing with tilting leaves is reflection's a shortwave, where it bounces and captures it better. Like it's any rough surface would absorb better than a smooth polished surface. In fact, that's part of the reason that polished metal is such a low emissivity. When polished metal oxidizes, like copper, it goes green. All of a sudden, polished copper is 0.03, it oxidizes and goes green, and now it's 0.9, because that surface is rough. So it's a similar thing to leaves, that it's the structure of the surface affects the reflection of shortwave.
It's just part of it also, the reabsorption of longwave, or reflection.
With vertical leaves?
With something off of normal.
Okay, let me add to this answer. We said 1,000 watts per meter squared for this. I actually never thought of this before. That only happens if this leaf is perpendicular to the sun. And the sun is only perpendicular to the ground at the equator at the right time of the year. So I probably should do this example with a flat leaf and an angle, because it wouldn't be 1,000. It'd be flat, and if it was really close to the sun, it'd be a lot less. So yes, that angle definitely matters, being perpendicular to the light source.
It's actually, it is 1,000 for a flat surface in the summer. It would go up and tilt it towards the sun.
Thank you. That's correct.
So it would be like 1,200 or something.
Yeah, that's right. And this brings us to an instrumentation tidbit that is not well understood by people. Let me go right here. When we build or use instruments, here's an instrument, and here's some white disc up here. I mean, they're various shapes of curved domes, but we say these are cosine corrected. And everybody says, okay, cosine corrected, that's good. What does that mean? It means that if you put a reference light here, you would get, let's say we did this and we got 1,000 watts per meter squared. Now we took that same light and we put it at some low angle. If this sensor still reads 1,000, it's not cosine corrected. It has to read less by the cosine of this angle. So at a low angle, the correct number might be, say, 100, the correct number. Now, if it reads 200, it's not cosine corrected. If it reads 50, it's also not cosine corrected. It has to be the right ratio of tilted radiation. So if we make a graph of this, there's one of these graphs on the Apogee website. I have to think this goes like this, and I think this graph is let me see. Nope, this is radiation here, and this is angle. So right here is 90 degrees, and that sensor should read 0 because everything's missing it. And here's 0 degrees, and this might be 100 or 1,000 depending on the units. So this is a theoretically perfect cosine response that says at each lower angle, the reading of the instrument should read somewhat less. And I used to think, many years ago, that all the instruments went like that. And they were wrong because they didn't capture the low angle right. And now I know it's just as easy to make a sensor that goes like that. You can get too much low angle light. You can underdo it or overdo it. And any instrument has to have the right optics to follow this line as closely as possible. The theoretically perfect cosine. Not too low, not too high. We calibrate our instruments right here. And then we hope all those angles are correct. And once you get it right for an instrument, it's reproducible. This, in the summer, most of the sunlight is in this range here. It's in high angles. And it's not too hard to get an instrument to follow this at these angles. It gets really hard to get the instrument to keep following it right to zero. And in fact, none of our instruments get this perfect. The highest end Kippenzonen instruments aren't perfect. None of them are, but they get close. They start to deviate right down here from perfect. And this isn't too critical because this is low angle light. There's just you might be off by 5%, but it's 5% of a small number. And over here, you better be right on because it's a big number. So this is cosine correction, and I think this speaks to your example of angles in here and what happens when you tilt things. How does it change it? But our instruments measure, it's by definition, what would the radiation be on a flat surface? And if you want to calculate the radiation on a tilted surface, you can, a little trigonometry, and like Mark just pointed out, if you tilt it, it goes above 1,000. But that's one way to explain the effect of tilted surfaces. And this is for an instrument, but you can also use this for any surface. What would it be tilted toward the sun? If you made your measurement flat, you could predict the increase in radiation from tilting it.
I don't need to draw this out too much so people know.
No, it's a good question.
The other part of that, though, is the transmittance. Because I don't know if there's any data out there that looks at the angular effect on transmittance. Do you think that the angle transmittance of that shortwave? Yes, really good question. And the answer is yes. And now let me answer that question. I got to race and give myself a tiny bit more room. In a leaf in particular. Here's our leaf. Now we're going to bring in a way giant microscope. And leaves are half air. And this marker, green marker, yeah, it's good enough. You get, this is some beginning plant physiology, and then you get stomates in here like this, and every plant biology book has a diagram like this. There's full of air, and these aren't probably quite as dense as I drew them. They're not touching. Now we have light coming right through, and it bounces around and it bounces out. And now we have light coming at an angle, and it bounces a lot more, and the transmission of light coming at an angle is way less. The reflection is more because it's a low angle, but the transmission is less. So we study penetration of light into leaves at different angles, and the lower the light, the less the transmission. So one part of this goes down and another part goes up, which is partly why we get away with saying 0.5, because there's some offsetting changes in this. But in general, the transmission at low angles goes down faster than this goes up. And in fact, when we get to whole canopies, you can imagine how much math you can do to try and analyze this with all the angles, and people have worked on that. But another way is just to put a net radiometer out there and just measure it and say, the sum of all these is this. And there's a theoretical treatment, and then there's the measurements. And if your instrument's good, you're going to nail these fluxes on this. This is a great example of why net radiation is so valuable, but
net radiometers are more expensive instruments, so few people use them. And when they don't use them, they're trying to model these fluxes, all of them. And you can measure this big one, and then you try to model the rest. And some years ago, Rick Allen, he was here at the university for many years. Now he's at Kimberly, Idaho, but he wrote part of a book chapter, and after testing, at the time, a bunch of instruments for net radiation, he said, these instruments have sufficient problems that it's more accurate to model the net radiation fluxes than it is to measure them. That's a sentence in that. It's a chapter in a book, I think. It's FAO 56. Since then, Blomqvist et al. Did a big study with a bunch of net radiometers, and as I recall, nearly all of the net radiometers were more accurate than the models. The only ones that weren't were the very cheapest models.
It was all, actually.
All, even the cheapest net radiometers. So that's the evolution of instruments. They're better and cheaper. And man, you can see, if you can get this number right with an instrument, wow, you're getting there, because now you just got a couple other components. But in my experience, if a user just puts the instrument out there without any understanding of all this stuff, they have no idea when they're collecting bad data. And if you understand the stuff, you can look at the lines and say, this can't be right here. And we better go check the instrument. And that's worth a lot to have that background. Devin.
So as I look at the winter over snow numbers, what are the inversions in Cache Valley? How do those numbers change with an inversion?
You would think they would have a huge effect on this. If you asked the true false to the population, you know, everyone said, well, duh, they have a huge effect on it. If you go out with our radiometers and measure this, there's hazy, right? So this is going to be less.
Minimal.
Wait a minute. Those inversions are 100, 200, 300 meters thick. When you look sideways at the mountains, you can see the haze. Now go out in inversion and look up and tell me if you can see the haze. It's not deep enough. You can't, the sky looks fine. You have to be looking through an air mass of several, 2 or 3 or 4 to see the haze. So this incoming shortwave is actually hard to measure. Hard to tell that there's an inversion based on attenuation of shortwave. We could, if we had one, 400 or 500 meters up and one at the ground, we could see it, but it's hard to see. But this tells you why we get cold inversions, snow on the ground, and we can't heat the ground up because there's snow on the ground.
So the emitted longwave, though, isn't from the sky also minimal effect from the...
Yeah, some, because there's crap in the air. But here's an example. So we keep studying the website, PM 2.5, and we say, wow, this is a terrible day. It's up to 50. What are the units on that? Well, micrograms per cubic meter. Wow, a microgram. I mean, a paperclip is a gram, and so this is a millionth of a paperclip per meter. It's the amount, the weight of the particles is tiny. And even though they're bad for our lungs, there's no doubt about that, the optical effects are smaller than you might think. So these fluxes don't change much from those. They change more with humidity. Humidity can be 3–4% of the, well, in the winter it might be 1 or 2%, but humidity is many orders of magnitude greater than the PM 2.5, and small changes in humidity would have a bigger effect than big changes in the particulate matter. But those are examples of this stuff that, you know, how would this apply to different things? Okay. Tomorrow we'll model planet Earth. I promised a key for E equals mc squared, which I already showed you, but here it is. And That's a good example of a question where you can't rely on your intuition to get the answer. You have to follow the rules and get it.
So are stovemates controlled by the infrared or by the short wave?
I can tape this back